Hi everybody. So today we're going to talk about hydrolysis. So hydrolysis is a reaction where a substance cleaves a water molecule to produce either an acid or a basic solution. The types of things that do this are typically ions, and they're ions of weak acids and weak bases for the most part. So if I look at something such as acetate ion, which we have here in the, we have a picture of here, we can see that this acetate ion can react with water to reform the acid that it came from. So essentially its conjugate acid, HC2H3O2. When it does that, it pulls a hydrogen ion off of the water and it produces hydroxide ion. So now I could write an equilibrium expression for this reaction. And if you look at it right underneath there, that's what we've done. Only I've used a Kb because the Kb, the acetate ion, is behaving like a base. So I labeled it as a Kb. I wrote my equilibrium expression, products over reactants. All right. Now the problem is that I don't have a table to look this Kb value up in. And so I'm going to have to rely on relating it to the Ka. So I want you to look at this reaction we just wrote. And then what we're going to do is we're going to write another reaction where we're going to look at the dissociation of acetic acid into hydrogen ion and acetate ion. And I wrote an equilibrium expression for that reaction as well. So now if I multiply the equilibrium expression for the acid times the equilibrium expression for the base, which I got from back here on this slide, I multiply them together, and what you can see is that the acetic acid and the acetate ion will cancel each other out, and what I'm left with is H plus times OH minus, which is what we've referred to in the past as the Kw of water. And so the relationship ends up being that if I know the Ka of a weak acid, it's Kb for its conjugate base. The two things would multiply together to equal Kw. So as Ka gets bigger, Kb gets smaller. So they're showing you a list here in this table of different acids and what the Ka is for the acid. So HF, 6.8 times 10 to the minus 4 is its Ka. All right. So the fluoride ion would have a Kb of 1.5 times 10 to the minus 11. And I would get that by plugging into this equation. I know Kw, I know Ka, I can solve for Kb. And what you can see is that as the acid Ka value decreases, the Kb value increases. So if you know one of these, you can calculate the other. So anions would typically react with water to reform the acid that they come from. So it's what we refer to as a hydrolysis reaction, and it leaves behind a hydroxide ion. So these anions, remember, are negative ions. They produce the negative part of water, hydroxide ion. Now, can you think of things that would be exceptions to this? What kind of anions wouldn't do this? And the answer to that is the strong acids. So anything that's a strong acid, the anions of the strong acids, those won't be able to hydrolyze because they're completely dissociated. There's no equilibrium constant. Cations can do the same thing. So only when they react with water, what they're going to do essentially is they're going to draw one of the hydrogen ions onto a water molecule, and they're going to produce hydronium ion and leave behind the weak base that they came from. So the cations of all of the ammonia type bases behave this way. And again, if you can write one of these, if you can write this for the ammonia, you can write this for any of the reactions. So the cations of all the ammonia type bases are going to behave this way. Now, other cations can also hydrolyze. So things that are metal cations, like iron ions and copper ions, those also have the ability to hydrolyze. What happens essentially is that they draw the positive charge is attracted to the negative side of the water molecule. So if you look at a water molecule, like here, all right, remember this oxygen side would be the negative side, and then the other side would be my positive side. And so the oxygen is drawn towards the positive cation, and it makes the link between the oxygen and the hydrogen on the water molecule a little bit weaker. And so it has a tendency to be able to lose a hydrogen ion. The bigger the charge, so +2 versus +3 would be a bigger charge, and the smaller the size of the ion make it behave more acidically. So typically these ions don't exist by themselves in solutions. I'm just going to show you a little picture here. So this is a picture of what happens with iron. So iron actually exists in solution. The iron +3 ion exists in solution with 6 water molecules attached to it. All right, and we refer to that as a complex ion. You can see the formula for it right underneath there. So what happens is another water molecule comes close to that, all right, and this linkage, this oxygen-hydrogen linkage, is weakened, and so it pulls the hydrogen off of there and creates a hydronium ion. And what will happen to iron ion will decrease in charge, so it'll go down to a +2, and I'll end up with an H3O+. Typically, we won't be working much with this type of a reaction other than for you to understand that they would be acidic. When you do the equilibrium lab, there is a hydrolysis question in there, and you might want to come back and look at this slide because you are specifically going to be working with iron +3 in that reaction. So these equilibrium constants for metal cations, this is a list of what some of them are. So you can see that the higher charged ions have a tendency, like iron +3, have a tendency to have larger dissociation constants, indicating that they would be more acidic. So in general, when we think about the things that have the ability to hydrolyze, all right, anions that come from a strong acid, all right, so chloride, bromide, iodide, nitrate, okay, they're the anions from a strong acid, those will not hydrolyze. If it's the conjugate base of a weak acid, it will hydrolyze and it will form a basic solution. And if it's a cation that's the conjugate acid of a weak base, it will hydrolyze and it will form an acidic solution. Okay, so that would hydrolyze and form an acidic solution. Cations of the strong bases like sodium, potassium, lithium, calcium, those won't hydrolyze. Other metal ions that we just talked about, those will hydrolyze and create acidic solutions. And then if a solution has both the conjugate acid and base of a weak acid and a weak base, it's going to depend on the relative strength of the Ka and Kb as to which one it will do. So what I want you to do is to look at each one of these salts, essentially. I want you to think about how they'll break apart. So I want you to write a dissociation reaction. So what ions will they break apart into? And then I want you to think about whether or not either of the ions has the ability to dissociate. Okay? So I'm gonna pause the video. Well, you should pause the video, all right, and try and do that. All right, so here's our dissociation reactions. So our salts break apart into the ions they're made from. So the sodium hypochlorite breaks up into a sodium ion and a hypochlorite ion. The calcium into a calcium +2 and 2 nitrates. And the ammonium chloride into ammonium and chloride, and the iron sulfate into iron and sulfate. So notice that the charges, because I'm starting with a neutral salt, the charges have to add up to 0 on the other side. So you should make sure that you can write these dissociation reactions. Now what I want to do is I want to look at those ions and decide if they can hydrolyze. So what I want you to do is to pause the video, look at each ion, and see if it fits into one of those categories we just talked about. If it won't hydrolyze, just cross it out. If it will, I want you to circle it, and then we'll decide whether it's going to be acidic, basic, or neutral. All right, so the sodium ion, the sodium ion comes from a strong base. So all the group 1 cations are from strong bases. It will not hydrolyze. But the hypochlorite ion is from a weak acid. So it will hydrolyze, and that solution will be basic. So when it hydrolyzes, it'll react with water to create a basic solution. The calcium, also from a strong base. It won't hydrolyze. The nitrate is from a strong acid. It won't hydrolyze either, so that solution would be neutral. In the ammonium chloride, the chloride won't hydrolyze. It's from a strong acid. The ammonium ion is from a weak base, so it will hydrolyze, and it will be acidic. And in the last one, the sulfate is from a strong acid. This is a metal cation. It will hydrolyze, and it will be acidic. So one of the things you can notice is that the negative ions are going to make a solution to be acidic if they hydrolyze, and the positive ions are going to make the solution acidic if they hydrolyze. I'm sorry, the negative ions make it basic. I think I said that wrong. All right, so the next thing that we want to be able to do is to actually calculate the pH. So not just to decide if the solution is going to be acidic, basic, or neutral, but to actually calculate the pH of a solution. So I'm going to show you an example of how we would do this on this slide. So this says that we start out by dissolving 28.5 grams of ammonium acetate in 2,500 mils of water. And we want to know what the pH is going to be. So the first thing I did is calculated the concentration, the molarity. So I took the mass divided by the volume and used the molar mass to get a molarity. The next thing I did is I wrote the dissociation of the salt. So in this first, I keep changing the thing, sorry. In this first line, what I've done is I've written the dissociation for sodium acetate to sodium and acetate ions. And if that's a complete dissociation, it's a soluble salt. So if the sodium acetate has a 0.14 molar solution, the acetate ion has a 0.14 molar solution. Now I'm going to write a hydrolysis reaction. So my hydrolysis reaction says the acetate ion reacts with water to reform its acid, acetic acid, and create a hydroxide ion. Now I'm going to set up my icebox just like we have before. I know the starting concentration of the acetate. I know the acetic acid and the hydroxide are 0. I let X equal the change in the hydroxide ion concentration, and I calculate the equilibrium concentrations of everything. Now I had to add another slide in here, so we're going to actually continue this on the next page. So I wrote my equilibrium expression. It's a KB, products over reactants. You can go back and look at the, I'm just going to move this. You can go back and look at the reaction we wrote on the last page. We're going to make our same assumption that X is much smaller than the starting concentration. So now what I want to do is I want to plug in the equilibrium values, but before I do that I have to calculate the KB. So I find that by using that relationship, that the KB times the Ka equals Kw. So I looked up the Ka for the acid that I reform. So I look up my Ka for the acid that I reform, the acetic acid. All right, that's the acid that I reform in the reaction. So I looked that up. Kw is 1 times 10 to the minus 14th, as long as I'm at room temperature. And it came up with a Kb of 5.6 times 10 to the minus 10th. So now I plugged in my equilibrium concentrations into my calculation, x squared over 0.14, because remember I'm ignoring x compared to 0.14. And I solve for x. X is my hydroxide ion concentration. So I get a POH and then a pH. So this is a typical way that you would do a problem that involves an acid. So I'm going to pause. I'm going to stop there. I'll post this and then we'll pick up here in the next segment of slides. You should go back and try that again. Go ahead and see if you can do this problem on your own.